Today's the 27th. All right, so first question here. We have a diagram of a set of point scatterers, seemingly periodic. And then I want you to derive the grading equation. And here I ask you to sketch appropriate rays and wavefronts, labeling all relevant parameters, showing how they lead to the equation. So basically I'm asking you to derive the grading equation. And so we did that, again, looking at this set of point scatterers here. They have some period of separation. And the way we analyzed it, we took and I started you out here with a pair of rays going to two adjacent scattering points and having a wavefront like that. And so, I mean, the whole idea for the grading equation is simply that the optical path difference is equal to a, well, we can call it Q times the wavelength, right? So whenever we have an optical path length difference that's an integer number of wavelengths, we're going to get enhanced scattering in that direction. So what I was hoping that you would do is something like we did in class. So here, if we have this wavefront here, and then we have a corresponding set of rays out here with another wavefront, all right? So we can see then that we have a delay. And so this is theta 1 and theta 2 out there. And I think, did I say that there's the same index? I didn't really say that, but anyway. Since I didn't put it, you could just assume it's 1 everywhere. So here we have, again, so the optical path length difference is, we can look at that from A, B, C here. And so we would have AB plus or minus, depending upon how you want to take this, AB minus BC is equal to an integral number of wavelengths, all right? And so, so I have to tell you something. I finally figured out a consistent way of looking at these orders and so forth. And so here, and perhaps maybe I'll touch on that. I wasn't holding you responsible for that in the test because I just figured it out prior to the test, actually. And so here, I'll do it this way for now, and then I'll just quickly show you what I was, I think how there's a inconsistency that's resolved in talking about this. So here we have AB minus BC, and so AB is equal to this period, which is that distance, times the sine of theta 1 minus the period times the sine of theta 2 is equal to an integer number of wavelengths. And so here you have the grading equation essentially is sine theta 1 minus sine theta 2 is equal to Q lambda over the period. So again, so there is a little bit of an inconsistency here, all right? So let me just briefly touch on that. And so the way you can resolve that inconsistency and the inconsistency is, if Q is Q positive or negative, and how does that correspond to the diffraction angle? So here, let's say we have normal incidence here, all right? So now if we have, so the zero order is going to go straight through, right? And now we have just sine of, let's say our diffracted beam is sine theta 2 is equal to Q lambda over the period, all right? So if now we have another convention, and that is that angles that are counterclockwise are positive, and angles that are clockwise are negative, right? So we can make that consistent if orders that go in that direction are positive. So this would correspond to our plus q direction, right? Because that, if this is plus, right, sine the again, that's going to mean that the angle theta 2 is going to be in the plus direction. All right. So and then if this q is negative, then that means that, you know, it's going in that direction, minus q. So there is a little bit of an inconsistency in my notes, and I'm going to clear that up. But I gave, either way that you did this was fine, okay? All right, because you could see here actually that if we want the path length difference, we actually want that to be plus, right? Because that'll be, you know, these two paths differ by the sum of those two, okay? Oh, I'm sorry. So there is a bit of an inconsistency, and I wrote up some notes to clarify that. It also came into play a little bit with the ray trace, but again, I gave you credit if you did it one way or the other way, so that you can do it with, you know, your notation showing this as plus or minus. So I gave it for either. Yeah.
So in a physical system, is there necessarily a way that we define positive or negative?
Well, what is positive or negative? I mean, in a physical system, right? I mean, it's a notation, right? It's a definition of what we mean. We could have equally described our angles as positive going in this direction, in clockwise, right? So it's not, you know, if we say that the physical significance is that we have counterclockwise angles, then, but that's kind of a arbitrary definition, really. So there really isn't, and we're going to have that same issue a little bit with the, so the grading vector, for instance, can point in either direction as well. So there's not really a way to resolve that one. But this one, for the grading equation as well as for ray tracing, we can resolve it and make it consistent with our angle rotation notation that we have. Okay. All right. So that was part A. Part B is we have this hologram formed with two beams at 488 nanometers in free space, as shown in the figure below. The angles are in the recording material that has a refractive index of 1.5. Okay, so we have a free space wavelength, we have an index, but there's no index difference between the region where we're doing the recording and not. So the question is, what is the orientation of the fringe planes relative to the z-axis? All right, so for that, so this one should be, I mean, I was hoping would be fairly easy here. For most of you it was. So remember always that here's 5 degrees and 10. So the fringe planes form along, and this is the z-axis, along the bisector of the inner beam angle. All right, so the bisector is like that. Okay, and that bisector is, you know, this total is 15 degrees, so the bisector is 7.5 degrees, which means it's 2.5 degrees below the z-axis here, or this is 2.5 degrees. Okay, and all your fringes are going to form like that. Okay, so again, so that's something you should remember. Okay, from interferometry or from this class, is that your fringes always form along that bisector. Okay, and then part 2, so that was part 1. Part 2 is compute the grading vector period and direction, and the direction of the grading vector. Okay, so you can get the direction in two different ways. Okay, one is through solving the k-vector closure relation that we may have. So here we would have, K1 minus K2 equals K, and we'll do that to get the period. But you should at least be able to get the direction of that K vector. You can get it pretty simply if you remember that the grading vector K is just perpendicular to those fringes, right? So now you have to figure out, so what is that direction? Well, it's either 92.5 or 87 minus 87.5. So it could either be this way or it could be that way. Okay, so the angle phi that we have for that grading vector direction is either, again, 92.5 positively or minus 87.5 in a negative direction. Okay, all right, so what about the grading period though? Okay, so for that, we're going to have to actually go and kind of brute force this a little bit. So here we have now that K is equal to 2 pi n over lambda in free space, and then we have the sine theta 1 in the x plus cosine theta 1 in the z minus sine theta 2 in the x plus cosine theta 2 in the z direction. All right? And then let's write this down here. So again, so this is 2 pi times 1.5, the refractive index over 0.488 microns. All right, and then we have sine of 10 degrees minus sine of 5 degrees. And that's in the, actually this is sine of minus 5 degrees, right? This is, again, a minus angle. And so that's in the x direction. And then we have plus cosine of 10 degrees minus cosine of minus 5 degrees. Okay, so a few people kind of missed the negative sign there, but that was our notation again for the counterclockwise and the positive and clockwise for the negative. So that ray is in the negative direction there. Okay? All right, so we, and then I got here, I end up with 2 pi times 3.074 times 0. So this is negative and negative. So we add those and we get 0.2608 in the x direction minus 0.0114 z direction. And then again, so K is, if we were to look at the magnitude there, K magnitude is, again, 2 pi over the period. And when we can multiply these, square these, sum them, and take the square root, and then multiply it by that factor. And we end up there with 2 pi times 0.8024. Again, this is inverse micron. So you don't have to multiply that out. If you did, it was 0.5041 inverse microns. And so you invert that, and that gives the period is equal to 1.246 microns. Okay. And then you can get the angle of that. If you wanted to get the angle, through this vector here, that would be the tangent of the x component over the z component, and that would give you. So if we took the arctan of 0.2608 over 0.0114, that should also give us these two angles that we have there. Okay, so you can get it either way. Yeah?
Kind of going back to part one of this, why are the fringes not oriented according to the direction of the rays inside the medium, like after refracting.
Well, they are, right? Because this was N, 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 N. There's no refraction.
I think that too.
Yeah,
Simple.
I tried to make it easy, but maybe if you did that, I don't think I took off very much at all.
Yeah, I mean, I was curious.
Like a quarter point.
So it's
maybe
just
or
saying
something.
N, N, N?
Yeah.
And they're all equal to 1.5?
They're all 1.5, which means there's no change.
Yeah.
So there's no.
I was trying to make it simple, but
No, I saw 1.5 and I figured the air wouldn't be 1.5.
yeah. Well, the 1.5 you needed here in calculating the magnitude of the or the grading period. Okay. So, okay. I tried. All right. So the last part here is a problem similar to what we had in the homework, where we're going to record an unslanted transmission, use an unslanted transmission geometry to record a reflection hologram. So here you do have your refractive index difference, okay? So again, I only wanted to test you once on that, so I thought I would do it here. All right, so first thing I ask is, okay, determine the gradient construction angles in air for the 248 beams. Also, draw the Bragg circle representation of the construction and reconstruction process and label K and the construction and reconstruction vectors. All right, so let's do that first. So this is part C, I guess, here. So here we have 248, which is set up again as a transmission grading. So you can see here, our fringes again are going to be like that for the transmission grading. And this then gives us a K vector. So this is the construction K1, 2 and K2, 2 for those propagation vectors. And this is our K. And so again, this is at 248 nanometers, 248 nanometers. All right, so, and then we want to reconstruct it as a unslanted reflection grading in that medium. And so here, again, for that is kind of the minimal closure that we can get with two vectors. All right, so here we have now a, say, a K22 and a K21. So does this bisector thing still apply? Well, yes, because we can think of this as having 180 degrees, and so, again, the fringes are along the bisector, except now, we just change our perspective and we're inside the medium, okay? All right, so, and this is going to be at 1540 nanometers for the reconstruction. All right, and here we have, this is what we want. We want to know what are these angles here, theta 1. They're equal angles. All right, so we can say now that we have K11, the magnitude of K11 equals magnitude of K12, and that is equal to 2 pi n1 over lambda 1. So n1 here is air in that case. And then here we have what we want is, so this is our angles in air, and this is going to be the 248 nanometers. And what we want is, or what we have is that K21, again, is equal to K22, and this is equal to 2 pi n2 over lambda 2. Now this is 1.5, and this is 1540 nanometers. And this here is going to be equal to I'm sorry, this one here is going to be equal to 1/2 K, right? All right, and so, yeah. So anyway, so, yeah. What am I, okay, so something is, no, I'm sorry. I'm getting screwed up. Yeah, this was right. Okay, this is 1/2 K, right? This is the 1540, the 1.5, and that's inside the medium. Okay. All right. So this, then we could write. We know what the value there is. So we have that's going to be equal to 2 pi times 1.5 over 1.54 microns, and that's equal to the 1/2 K, and and so we have our number for that, but we don't really have to multiply it out yet. And this here is also going to be equal to K12 magnitude times the sine of the angle in air, all right, that we need at the 248 construction, okay? So here again, so we don't have to multiply out the 2 pi's, for instance, here. I usually don't like to do that unless I have to. So we can say this is 2 pi times 1 over 0.248 times sine of theta is equal to 2 pi times 1.5 over 1.54 microns, okay? And so we end up with the sine theta is equal to about 14 degrees, 13.98 degrees in air. Okay? So we really didn't even have to do the Snell's law in that case as well. Okay, but we needed it for the magnitude of that propagation vector to get the grading vector right. Okay. Okay, so that was problem number 1. And problem number 2, we have some image analysis here. All right, so here we have, again, a hologram is formed with an object beam placed here at position 1.5, 0, and -10. And then we have it's formed with a collimated reference at 10 degrees, okay? And then, and that's 10 degrees to the z-axis. The hologram is reconstructed with a plane wave at 12 degrees to the z-axis with the same wavelength. So that, I guess that came up a little bit, but the wavelengths are equal, all right? And the hologram is located here at z equals 0 with an x position of 1 and a y, and we're looking at a point on the hologram that's in the xz plane, all right? So the first question is compute the direction cosines of the image ray that is diffracted from the point H on the hologram plane that corresponds to the +1 diffraction order, okay? So here's our point. So we need to first form the direction cosines for the construction rays and the reconstruction rays, okay? And then from that, we can use the ray trace relation to get the image direction cosines, all right? Okay, so first off, we have let's look at the reference beam. So that has an angle of 10 degrees to the z-axis, but if we want to calculate what the L direction or the L cosine relative to the x, so we're actually going to take the LR is equal to the cosine of 80 degrees, right? Because that's the angle relative to the x direction if we had 10 degrees relative to the z direction.
The other one with respect
here's x, here's z, right?
Yeah.
So we have,
I think we're dealing with the reference being on all.
yeah, I'm doing the reference beam here. So here's the reference beam. So this is alpha I, this is gamma I, right, for that,
So that should be 80.
for that ray. So this is 10 degrees, so that's 80 degrees.
Right.
Yeah. So
The other one, 12? I'm talking about LP.
that's the reconstruction beam.
Right.
Yeah, this is the reference beam that I'm doing first. Okay, and then, you know, so of course MR is equal to 0. It's equal to 0 for all of these. NR is equal to the square root of 1 minus LR squared. Okay, so this is equal to 0.17365, and this is NR is equal to 0.9848. Okay. Now, okay, so now the reconstruction beam, or so this is R, and this is P, so we have LP, so that one comes in at 12 degrees. All right, so that one is 78 degrees. We take the cosine of,
Isn't it 12 then? That's what I was saying. Isn't it cosine of 12 degrees?
well, it's the same thing here, right?
It's still from the z-axis of the diagram.
So this
With
is,
respect to the x-axis, LP?
these are all with respect to the z-axis.
But, yeah, so it's,
Here's the ray. There's 12 degrees relative to the z-axis. Here's the ray.
Is it with respect to the x-axis though? Do you take LP with respect to
yeah,
the
so
x-axis?
relative to x is
To get,
28, which is
yeah,
L is the
to get the direction cosine, right, you need alpha, which is, you know, the angle between the x-axis and the ray. And that's 78 degrees. This is 78, this is 12.
I thought LP was 12.
I know, I remember, yeah. I was trying to figure out why you did that, because you got the first one right. I mean, you got LR right,
Right.
but then you switched it, unless the image, unless my diagram looked a little confusing, but
I think it might have just gotten confused because your 12 is like underneath it.
yeah.
But your line is above it.
Well, I know, did anyone, no one else seemed to have that problem, so, sorry. But, you know, maybe I'll draw it differently next, maybe I'll draw it over here, like this, or something, to make it, yeah.
So, can you do, so in the previous, if you go back, for NR, couldn't you also do cosine of 10 degrees and get the same answer?
No, you can't, because,
It is the same, like I just checked it. And that's what I
well,
did.
it's probably the same because MR is 0.
Exactly, so I assumed that,
Yeah.
and like used that relationship.
Uh,
And I got the right answer, and I just lost 0.5 points for doing that method.
0.5.
I know, it's like silly, but like,
Well, no, I mean, that's actually, I mean, well, come and see, that's, you know, it's actually,
it's only because.
it's actually incorrect because, you know, L squared plus M squared plus N squared equals 1. And if you do that, this relation is no longer holds in the case where you have a non-zero M.
Exactly.
Yeah.
There's zero.
So,
I understood that it was because it was infinite, but it's like more directly, it seems more direct to just get the angle with respect to z, because that's like the direct definition of a direction cosine. And you know that it's 10 degrees, like that's defined.
yeah, I don't know. I guess why don't you see me, because I think that would be okay in this case, because that's actually the gamma that you have in it. All right. But in general, you definitely need that. So I don't know if anyone else did that too. I can come and see me afterwards, because I can give you credit for that, since in this case it does make sense. Okay, so let's do the rest of LP there, or the MP of course is 0, and then NP is, again, square root of 1 minus LP squared. and that's equal to, so this is equal to 0.2079 or 2.208, and this is 0.97815. Now, let's look at the object wave. So this one caused a little bit of problem for a few of you because the point is at 1, 0, 0 on the hologram plane, but the object point is at 1.5, 0, and minus 10. All right? So remember the definition, if you have the coordinates, is L0 is equal to xh, right? The hologram plane minus xo over that distance, that's O. And so O is equal to square root of xh minus xo squared plus yh minus yo squared plus zh minus zo squared. All right, and so this is 1 minus 1.5 squared, that's 0, and then we have 10 squared, square root of that, and that's equal to about 10.0125. Okay? Now, the problem came about because, again, we have xh minus xo. So xh is 1, xo is 1.5. So this is actually minus 0.5 over 10.0125. All right? A lot of you forgot that minus sign there. So, which was, I took off a little, like a quarter point or something for that. But then I tried to track what you did after that with the wrong number to give you credit if you did it the right way from that point onward. So I only dinged you once for that amount, hopefully. If not, let me know. So at any rate, so now the LO is, this is approximately equal to minus 0.05, right? That divided by roughly 10. And NO is equal to 0.99875. Okay. So now the in order to get the image direction cosines, which was actually what the question asked, we have Li is equal to Lp minus Q lambda 2 over lambda 1 times Lr minus Lo. Okay. So anyway, so here if we just substitute in the numbers there, I ended up with a Li of minus 0.01568, and that's equal to cosine of alpha I, and of course mi is equal to 0, and ni square root of 1 minus Li squared, which is pretty close to 1, 0.99988. All right, so alpha I here, alpha I is a pretty large angle. I got, that's equal to 90.896 degrees. Okay, so the second part of this question is you have this ray which diffracts. Let's just draw it separately. So here we have, was that part C or part 2? Okay. Okay, so here's the situation. So we have this, and we have this point 1 up here on the hologram plane, and so we're illuminating it with this angle, again, which is like 12 degrees. for the reconstruction. And then we get a diffracted angle, which is just a little bit more than 90 degrees, okay? About 0.9 degrees more than 90. So it's a very shallow angle that goes like that, all right? Now, what I'm asking for is what is the intercept here at this location, all right? So this is not the image location, all right? This is just the intercept of where this particular diffracted ray would cross the z-axis. So let's call that something else here. It's not really zi, it's zq. This height here is 1, but we can solve it kind of the same way that we did in class when we were looking for the image distance, right? Because now we have this angle here is alpha I equals 90.896, and that angle here is, this is going to be simply this 0.896 degrees, right, for that angle. All right, so if we want to find, say, ZQ, that we can say tan of gamma I is equal to 1 over ZQ. And so ZQ, oops, is equal to 63.94 centimeters, okay? All right, so that's fine. However, if you did it, if you took your imaging relationships differently, all right, so what I mean by that is if we had L, so let's say if we now have, instead of taking Q positive, if you took Q negative here, assuming that or had this as a positive here and did the calculation doing that, we would then have that Li is equal to 0.4316 equals cosine of alpha I. All right, and Ni is equal to, again, square root of 1 minus Li squared, and that's equal to 25.57 degrees. So in that case, you would have something quite different here. So here again is 1. We would have a gamma of 25.57 degrees, okay, out here. So the intercept in that case would be in the negative space, and it would be minus 2.09 centimeters. So again, these don't correspond to the image distances. They just correspond to the positions where you have the intercept of that ray with the z-axis. Okay. So the question is, which is the correct, which is the right one? Okay. Well, again, we can refer this back, remember, to that the grading vector question or problem that we had earlier, and our direction, having our directions in the counterclockwise direction giving us a plus angle, the counterclockwise in a plus and a clockwise in a negative. So in that case, if we have, if we chose this, right, or if we have LO minus LR, lambda 2 over lambda 1, and here we would have Li minus LP, and this is our Q. So here again, so here we would have the ray trace relationship giving us a, if Q were negative, right, if this LP were 0, Q were negative, then we would get a clockwise rotation here, and then if it were positive, we would get a counterclockwise. So we can just deal with this, we don't have to change it right now. I think the relations I gave you are fine. It's just they're not quite consistent with the clockwise and counterclockwise notation. So I will adjust those, but we can just work with it as we have been. And if you do it one way or the other, going forward in this during this class, it's fine. Just because I kind of laid it out a little bit ambiguously to begin with. So I just wanted to point that out to you because I don't know if any of you had that question, but it was troubling me the last week actually, and so I finally worked it all out. All right, so part 3 on that question is compute. Now let's look at the secondary paraxial image, which is x4, y4, z4. All right, so y4 is going to be 0, and we simply have that z4 is equal to zp, zo, zr over z0, zr minus mu zp, zr plus mu zp, zo. All right, and so here, if we zp and zr are at infinity, right? So if we divide top and bottom by the product zp, zr, we then have z0 over zp, and again the wavelengths are equal, so we have minus 1. This term drops out, and then we also have a plus z0 over zr, and that goes to 0 and that goes to 0. So z4 is just equal to a minus zo, okay? So it's plus 10, since zo is negative 10. And then for the x4, that's equal to xp, zo, zp, zr, minus mu xo, zp, zr, plus mu xr, zp, zo, that divided by z0, zr, minus mu zp, zr, plus mu zp, zo. And so whenever you have this infinite distance, it's best just to divide out by that particular distance, because that's going to cancel some terms for you. So here, if we divide by zp, zr, we end up with xp over zp minus mu xo over zo plus mu xr over zr divided by, we're going to have, actually I divided out by zp, zo, and zr. And so here I have 1 over zp minus mu 1 over zo plus mu 1 over zr. So again, so these go to 0. These are not 0, right? These are the tangents. This is the tangent of 12 degrees, and this is the tangent of 10 degrees, okay? Some of you said those went to 0, but they don't go to 0. And so when you sub in that, we know xo and zo, mu is equal to 1, and so this works out to be 5.39 centimeters, okay? So that's our secondary image. So we see that one also is on the plus side, but it's way far different from that distance, again, because that's a different value that I was asking for. Okay. Now there's another way you could solve this, although it would have been wrong in the sense that it's not the right way to solve it, and that is just use the grading equation. You can use the grading equation there and calculate what that diffraction angle is, and see that you end up getting the same intercept. Okay. So I think maybe if I give this problem again, or some version of this problem again in the future, instead of asking for X4 or the secondary paraxial image, I may ask for solve this by the grading equation, which would give you the same result. So it would be kind of confirming the previous result. I was a little afraid that if by asking this, I was going to say, oh, why didn't I get that answer in there? I better go back and change that. But not too many people freaked out, I don't think, because most of you knew just to sub in that. Did I confuse anybody in doing that? Okay. All right. So the last problem is we have two parts. I thought I should ask something about the aberration, since we spent a lot of time on that. And so I was a little, I thought everyone should get the first part, and unfortunately not everyone did. Okay, so all right, so here we have these two configurations, one with this point source on axis, and it's constructed with an off-axis plane wave, and this one has an off-axis point source, also constructed with those same off-axis plane waves and reconstructed with a slightly different plane wave angle. All right, so the first part of the question here is I ask, which of these two is a better configuration? Okay, and we actually went over this problem in class, and this is the better configuration. Okay, this part on the left is the better configuration, because the aberrations that you get are minimized. All right, they're not zero, but again, by putting this point on the axis here, you are eliminating some of the off-axis aberrations, or greatly reducing them. And as we saw, it actually greatly reduced the astigmatism in that problem that we went through in class. Okay, so if you have this, notice here you have this distance, and that compounds or is a factor in the aberration coefficients, in almost all of the aberration coefficients that you have, except for, well, distortion, I think, is the only one where it's not. But at any rate, this again was I was hoping that everyone got that. And again, you should remember that if you have that option in a setup, always try to form the point source on axis or close to it, and that'll immediately help to minimize some of the aberrations. Okay, that was part A. Part 1 of part A. Part 2 of part A is this one here. So here is this spherical aberration coefficient. I'm sorry, the aberration that is not affected by the X is the spherical. So here we can see that this only depends on the axial positions of the points that we have. All right, so these are all point values that we know from the construction and the reconstruction geometry. And this is the secondary paraxial image point. And we just went through and calculated that in the previous problem. So the question is, for the holographic lens shown above, R and P are point sources at infinity. Derive the relation that shows that when lambda 1 equals lambda 2, the spherical aberration coefficient is 0 when R and P are point sources at infinity. So here we have these reference and the reconstruction sources are point sources at infinity, giving us a plane wave. And how does this coefficient, why does that coefficient go to 0 when mu is equal to 1? All right. So not too hard. All you have to do is solve Z4 and then sub that in. All right. So let's go ahead and do that. So we have that, first off, S4 is, again, so this is equal to 1 over ZP cubed minus mu over Z0 cubed minus mu over ZR cubed minus 1 over Z4 cubed. All right, so ZP and ZR are at infinity, so these terms are both 0. And so we have minus mu over ZO cubed minus 1 over ZO or Z4 cubed. All right, so when does that term go to 0 is basically what I'm asking. So let's look at Z4. Again, this is equal to ZP, ZO, ZR over ZO, ZR minus mu ZP, ZR plus mu ZP, ZO. So again, if we divide by ZP and ZR, top and bottom, so this becomes over ZP, that goes to 1, or I'm sorry, yeah, that goes to 1, and this is ZO over ZR, so this goes to 0, this goes to 0, because ZP and ZR are 0, and we're simply left with minus ZO, or minus, I should say, in general, this is going to be Z0 over minus mu, but since mu is equal to 1, this is minus Z0, okay? And so if we substitute that in, a lot of you just said, well, okay, so it's, this is 1 and that's it. But if you recall, in class we had minus, and I gave you full credit for that, but I just wanted to go through the full derivation here. Minus mu over ZO cubed minus minus mu cubed over ZO cubed when we substitute in for that Z4. And this is now minus 1 over ZO cubed times mu minus mu cubed. And if you remember, I wrote this as mu times mu squared minus 1, if we bring in that, and this is 1 over ZO cubed. So when mu is equal to 1, that goes to 0. That spherical aberration term goes to 0. Okay, any questions on that? All right. Okay, and then 3b is the spectrometer question, kind of. Okay, so here, here again we have a grating placed next to a lens. We illuminate the grating here at 30 degrees and we diffract light off along the axis, and then it comes to focus here in the back focal plane of the lens. And so I ask you, give you some parameters here, and I ask you what is the minimum wavelength difference that can be detected at the lens focal plane if the peak of the diffraction pattern of the second wavelength falls on the null of the diffraction pattern formed with the construction wavelength, or the 550 nanometer light. Assume that the incident light at the new wavelength is also at 30 degrees to the z-axis, and that the lens is large enough to collect all the diffracted lights. Sketch the diffraction patterns for the two wavelengths at the focal plane near the z-axis. All right, so the two patterns are going to be, so if that's for lambda 1, the second pattern is going to fall on that 0. So that's lambda 2. And that's our criteria, all right, for those two. So what we are looking for is the width or the radius, I should say, of this diffraction pattern, because that's then going to set the angle here, the new diffraction angle, say, for the second wavelength, all right, that can be discriminated or detected relative to that first, according to our criteria. So let's solve that. Okay. All right. So we have then that that delta x, all right, just draw that a little bigger there. So here's our airy disk pattern, and so this is the delta x that we need, and that's equal to 1.22 lambda times focal length over the lens diameter, and so that's 1.22, 0.55 micron times 10 centimeters over 5 centimeters, all right? And that then works out to be 1.342 microns. All right, and that is so the first diffracted beam is going off at, so theta 2 is 0 degrees with our grating that we have. When we come in at 30 degrees, we diffract off at 0 degrees, and theta 2 prime is now going to be determined by the tangent. Theta 2 prime is equal to delta x over f, and so this is a pretty small angle. Theta 2 prime equals 7.69 times 10 to the minus 4 degrees. Okay, so it's small, but our grating could supposedly do that. So now so now we have to figure out what wavelength difference this small angle corresponds to, and for that we could use the grating equation. All right. So first off, we have to find what so we're going to have sine theta 1 minus sine theta 2 is equal to lambda over the period. So we need to find out what the period is, right? So if we put initially, say this sine theta 2 is now going to be equal to 0. This one is 30 degrees, and that's 0.55 microns. All right, we end up with a period of 1.1 microns. So that's the same period for the grating that will be used during the reconstruction phase. And we also have that in the reconstruction we're using the same reconstruction angle of 30 degrees. So we have now sine of the same theta 1 minus sine of theta 2 prime is going to be equal to lambda prime, a new wavelength, over the same period. Okay. So we then have 1.1 micron times sine of 30 degrees minus the sine of this really small angle but non-zero, 7.69 times 10 to the minus 4 degrees, and that's going to be equal to our new wavelength. And that new wavelength, lambda prime, is equal to 0.549985 microns. So it's really very close to 0.55, and the difference, delta lambda, is 1.476 times 10 to the minus 5 microns, or 0.01476 nanometers. Okay, so it is a very small wavelength difference that can be detected with that system, in part because we have, this is 10 centimeters, and so, if you buy a spectrometer, the bigger the spectrometer, the more it costs, and that's the reason, because you're getting much better resolution, but all of the optics have to be, very well done and stabilized if you're going to be detecting small differences like that. So anyway, so that was the exam. Any questions? All right, not too many wailing and gnashing of teeth. So all right. Well, we have some time left, so let's get back to where we were. Refresh our minds here. So we were talking about coherence, and we have a temporal coherence that we were talking about, and for that we have a wave, and basically we sample the wave at two different points, P1 and P2, and measure the field there, VP1 and VP2, and we see if the phase difference, P1, P2, is basically a constant, if it's not washing out. If it is constant, then we say that we have temporal coherence. The temporal coherence corresponds to a propagation along the direction of the wave propagation. And so we have a length L coherence, which is also related to a temporal coherence time as such. We also have a spatial coherence, and in that case we have a wavefront, and we basically sample that wavefront at two different spatially separated distances, and that gives us a sense of what the spatial coherence is depending upon that separation distance. Okay, and so we developed a term for quantifying this that we call the complex degree of coherence function, and basically it represents a kind of a convolution between these 2 points. So we have a gamma 1, 2 of this coherence time, tau, and that is, again, so if we have VP1, we measure the field at point P1 here at some time, so we have t plus some delta tau later, and then we have VP2 star of t, take the time average of that and normalize it, so we have VP1 of t, VP1 star of t, time average of that, and VP2 of t, VP2 star of t, time average of that, and we take the square root of that. So this was our definition of the complex degree of coherence function, and we saw that this is not just a artificial term. We can actually get a relationship between this gamma 1, 2 of tau, say the magnitude of that, and when we set this is basically the intensity or the intensities of the two fields, and so that is related when these intensities are equal. This is just equal to the visibility, which is equal to I1 minus I2 over I1 plus I2. So we get a very real physical characteristic for that complex degree of coherence function. And in addition, we find that if we have sources of different characteristics, so if we have, say, a Gaussian source, the coherence time that we have is inversely related to the width of that full width half maximum delta nu for that spectrum. So here is, say, a nu 0 or a average nu, as we called it. And so we get a kind of an inverse relation, 1 over delta nu times a factor. For the Gaussian, that factor was the square root of 2 ln 2 over pi. And this works out to be about 0.664 over delta nu. For a, if we have this curve, a Lorentzian function, the coherence time in that case is just 1 over delta nu again times 1 over pi. So this is about 0.318 over delta nu. So this is the Lorentzian is a broader curve, and so the coherence time is less for that system. Here again, so here are these different functions that I'm drawing. So here's the Gaussian, here's the Lorentzian. We can also have this ideal kind of rectangular function like this, and that the rectangular function, which is kind of a mathematical construct since we don't really have a source like that, but it also has this same form, which is 1 over delta nu. So that's the important thing here, that if we know the spectrum of that source, we automatically know what the coherence length for that source is. Okay, so those are kind of gas emission sources. The next thing I wanted to discuss, though, was running out of note paper here. The next thing I wanted to discuss is what if we have a laser? All right, so we have, for a laser, we have a gas emission. All right, and let's say if we have a Heine laser, so we're going to have we have this Gaussian kind of gain profile for that source, and the laser, here's our gain medium here, and when we make a laser, we have put a couple mirrors on there, and what the mirrors do is it gives us feedback, and the feedback is necessary because what we want to do is, after we have this field e to the minus j beta, or k, called kz minus omega t. So after this field propagates one full distance, we want to have the same phase relationship here. So we want the mirrors here are spaced at a distance L, and that phase matching will occur and giving us a frequency difference here, delta nu, between the the frequencies, which is c over 2L, this cavity length. And so these frequencies that are allowed now, instead of being this Gaussian, which is extended, are something that looks like a delta function. They're not quite a delta function. That are these frequencies here. This is frequency, and this is c over 2L spacing, and there are going to be, these continue on, but I'm just drawing them here as equally spaced frequencies. So the only frequencies that are actually allowed are the ones in which this this mode frequency overlaps with this emission profile. And these are not actually delta functions. These mirrors aren't perfect. There's a little bit of instability. So there are actually going to be a small spreading of these. But for now, we can consider these as delta functions. Okay. So as long as, again, as long as this might be, say, a loss line, you have to exceed the loss in order for the mode to oscillate in the cavity. And so let's say we have only 2 modes oscillating for a laser. All right, so how does that change the coherence length for the laser? All right, so that's the question that we're going to answer next time. And we'll see that actually it's related to this mirror separation distance that we have, and we can kind of get a sense of how many modes we can oscillate or what the coherence length is simply by knowing if there's only, say, 2 modes in the laser or 3 modes and so forth. We can immediately figure out what the coherence length is for that particular laser. Okay, so we'll see you on Thursday.